Yeah, good morning, dear students. This is Dr. Vijaya Babu. So, in continuation with the previous lectures of network analysis, so I think we have solved the concepts of KVL, how to apply a KVL in a loop, and also we have understood how to apply KCL at the node, right? So, I think we have solved some of the problems on it. Now, whenever the network analysis problem is given, okay, so sometimes he will be asking the branch currents, sometimes he will be asking the nodal voltages. So to get those concepts or to get the solutions, so sometimes it really difficult for us with only the concepts of KVL and KCL. Usually, all the most of the problems we can solve with KVL, KCL, voltage division, and current division principles. But sometimes in some problems, okay, so some problems are really critical. Even though we apply those concepts on those problems, so it is very difficult for us, that the problems are very challenging and it is very difficult for us to get the solution of them. So in such cases, so one of the very important concept, that is the delta to star and star to delta conversion, really will help us in making the solution to go ahead. So okay, so now this lecture will try to deal with the concept of star to delta and delta to star conversions. So now, so this is something like delta to star and star to delta. So this is the conversion we need to make. Sometimes delta will be given, you need to convert into star. Sometimes star will be given. So that means some portion of the network will be in the form of delta. So that means simply I can tell you. So some portion of the network will be in this shape actually. So let us consider this is RA, this is RB, and this is RC. So in this combination with a delta RA, RB, RC, sometimes it is required to convert this into a star connection. Okay, so that means star connection means I will try to show with this color. See here with the blue color. See here. So this resistor, and this resistor. That means let us consider this node is 1, this node is 2, and this node is 3. Okay, so that means you need to remove the 3 resistors RA, RB, RC, and you should be able to connect the resistors R1, R2, R3, something like this. So you should be able to connect what? R1, R2, R3. This makes the problem simple, and then you can go ahead with your normal approach. So then what is the relationship between this RA, RB, RC and R1, R2, R3? So before going ahead for those relation, so I would like to continue with the star to delta connection as well. Star means, so he will be giving what? R1, R2, R3. So we'll be giving R1, R2, R3. So in this context, between the same nodes, let us assume this is 1 and it is 2 and it is 3. Within the 3 nodes, among the 3 nodes, you need to remove all these resistors and you should be able to connect a delta. So a delta, something like this. Okay. So that this will make the problem very simple now. And I'll try to consider this as RA and this as RB and this as RC. So in this problem, we need to calculate what is RA, so what is RB, what is RC. So what is RA in terms of given R1, R2, R3, RB in terms of R1, R2, R3, and RC in terms of R1, R2, R3. So that you should know. Okay. So to convert a star network into a delta network. So now I'm going ahead. Here, what are the unknowns here? So simply R1 we don't know, R2 we don't know, and R3 we don't know. So we need to calculate what? R1, R2, R3 in delta to star connection, okay, in terms of RA, RB, RC. So usually for the students, I have a simple shortcut formula to remember this delta to star and star to delta. So I think everybody have seen this triple R movie, right? So from that movie, from that triple R combination, so I can simply make it as RR by R. So this is the formula what you should use to convert delta to star and star to delta. With the same formula you can use here. Okay, so immediately you can ask me, so why it is required to use the same formula? So it is not like that, dear students. Here you have a sigma in the denominator, whereas here you will be having the sigma in the numerator. So only that is the difference between delta to star and the star to delta conversion. It is a very shortcut formula. Easily you can remember it, right? So going ahead, so now that means, so I can write it as simply R by R plus R plus R. So this is the context. This is how you need to apply the logic here. Similarly, the logic how you will apply here, it is RR plus RR plus RR divided by R. So this is the magic in delta to star and the star to delta conversions. So now on understanding this shortcut formula, I will try to write the original value of the conversion now. So first of all, I want R1, right? So I want R1. So for R1, you try to take the adjacent resistors. What are the adjacent resistors of R1 here? RA, similarly RC. So RA and RC are the adjacent resistors of R1. So that means it is simply RA, RC divided by sum of all the resistors. That means RA plus RB plus RC. So this is how you need to understand the value of RA. So once you have written R1, it is very easy. You can easily write the values of R2 and R3 as well. Okay, so that means R2 is equal to, so the adjacent ratios of it, RA and RB divided by, so what you can write here, so RA plus RB plus RC. Similarly, you can write the value of the last resistor, that is R3 in the star connection. So which is equal to, in terms of deltas, that means RB, RC divided by RA plus RB plus RC. So this is how beautifully you can easily convert a delta network given into a star connection. So similarly, the same logic I will try to apply for star to delta. So that means first of all, I need RA, right? In this context, I need RA. So I'll try to use a different color to have a clarity. So you want RA now. So RA is equal to, so RR plus RR plus RR. So the logic is very simple. So that means R1 R2 plus R2 R3 plus R1 R3 divided by, okay, you have a single resistor. So that single resistor must be opposite to RA. Okay, so opposite to RA. So this is RA. Now what is the single resistor opposite to RA? R3. Okay, so that means this is something like R3. So this is how very easily you can convert a star network into a delta network, right? So going ahead, similarly, I have done with RA. Now I'll try to go with delta RB. So in delta RB, RB is equal to, once again, the numerator is same for all the values. So that is R1 R2 plus R2 R3 plus R1 R3. Okay, so divided by, okay, so the opposite of RB. So what is the opposite of RB? You have here R1. So opposite of RB is what? R1. So this is how you can do it. Similarly, the value of, lastly, the value of RC, the value of RC is given as R1 R2 plus R2 R3 plus R1 R3 whole divided by the resistor opposite to RC. So the resistor opposite to RC is what now? So it is simply R2. So this is how very easily you can convert a delta connection into a star connection. Okay, so we'll try to solve a simple problem uh, uh, depending upon these conversions. So let us take, so first of all, delta to star, right? So let us assume this is the delta connection. So what he has given, so let us assume this is 1 ohm, this is 1 ohm and this is 1 ohm. So he is asking to convert into star connection. So convert, the question is convert following delta to star? So this is a question. Okay, so now how will you convert it? So you want this, this, and this. This is a star actually. So take it as R1, take it as R2, take it as R3. So finally, from delta to star conversion, you have a triple R formula, RR by R, but this R is what? Sigma R. Okay, that means simply R1 is equal to, so every resistor is 1, so 1 into 1 divided by 1 plus 1 plus 1. So simply 1 by 3 ohm is the answer. So similarly R2, however, you will be getting the same thing. R3 also will be getting the same thing. So this is how you can convert the delta conversion into star connection. Okay, so that means if you ask me to redraw this, so R1, R2 and R3. So whereas this value is 1 by 3, this value is 1 by 3 and this value is 1 by 3 ohm. So to check whether this is correct or not, one thing I try to do, I try to convert back this to once again to delta. That means I got this as a star na. So this star I'll try to convert back to delta. So let us assume, so what will be getting then? So that means this is delta. I'll try to consider it as something RA. Okay, so I'll try to consider it as RB and then this is RC. So convert this star into delta in terms of RA, RB, RC. Once again the same triple R formula, RR by R. Okay, but here the numerator is upside. So that means if you want the value of RA, so it is sigma RR. So that means 1 by 3, 1 by 3 plus 1 by 3, 1 by 3 plus 1 by 3, 1 by 3. You have dot. Okay, it is a multiplication divided by what will be having finally? You will be having a opposite resistor. So opposite resistor is what? So RA opposite resistor is what? This one, right? 1 by 3. So take it as 1 by 3. Okay, that means you try to simplify this. So 1 by 3, 1 by 3. So 1 by 9. How many times? 3 times divided by 1 by 3. So 1 by 3 by 1 by 3. Answer is 1 ohm. So exactly we have started with 1 ohm. So once again we come back to 1 ohm. Similarly you can calculate, you can prove that RB and RC are also equal to 1 ohm and 1 ohm. So this is how very simply you can apply the concept of delta to star conversion and star to delta conversion. Okay, so in the concepts of network analysis. So whenever you did not get any idea to go ahead, okay, so with the basics of KVL, KCL, voltage division and the current division principles, okay, immediately you can have a look over this delta to star and star to delta conversions. This may help you to make the problem very simple and the solution will keep on going. So this is how you can utilize the benefit of this delta to star and the star to delta conversions. Okay, so thank you for giving this opportunity, dear students. So we'll try to do some more problems on it in the next session. So thank you for giving this opportunity.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.